can solve some relatively simple exponential equations if we can get everything into powers of the same base. And then we just use the laws of exponents to help us answer the question. When we come back in January, we'll be solving much fancier equations by asking the calculator to put them into powers of the same base. So the deal is, we have two different bases here. We want to come up with a common base, some number that when you raise it to a power, you get 2. You raise that same number to a different power and you get 8. For number 1 here, common base would be 2. Because we can take 2 to a power and get 2, we could take 2 to a different power and get 8. So we're going to rewrite each base. 8 is 2 to the third, 2 is 2 to the first, which doesn't change anything. And then substitute. Just substitute those values into the original equation. So instead of 8 to the x, we're going to replace it with 2 to the third to the x. And of course, this one's just going to be 2 to the first to the sixth. So powers of powers, we have 2 to the 3x equals 2 to the sixth. Now we got the same answer. These two are supposed to be equivalent. And we have the same base. The only way that can happen is if the exponents are the same. So 3x has to equal 6, which implies x equals 2. We can check that. 8 to the second is 64. 2 to the fifth is 32, so 2 to the sixth is also going to be 64. And that checks out. For number 2, we actually have two possibilities. For our common base, we could use either 9, because 9 is a power of 9, and 81 is a power of 9. Or we could choose a common base of 3. We could write 9 as 3 to the second. We could write 81 as 3 to the fourth. I'm going to go with 9 just because I think it's going to be easier. So 9 is going to be the same as 9 to the first. 81 is going to be the same as 9 to the second. Just going to replace those. Well, there's not much to replace here. We'd have 9 to the first raised to the 4x has to equal, instead of 81, we're going to replace this with 9 squared. So we have 9 to the 4x equals 9 to the second. The only way that can work is if 4x equals 2, which implies that x equals a half. Check it out. We put a half in here for x, that would be 9 to the 4 halves, or 9 to the second, does equal 81. Number 3, we already know the common base. It's the same as it was on number 1. The common base is 2, so we can replace the 8 with 2 to the third being raised to, and I'm going to stick an extra set of parentheses in here. And then this would be 2 to the first raised to the x plus 1. Powers of powers. We're going to multiply these exponents. So we have 2 to the 3x minus 3 is going to have to multiply these exponents, which doesn't do much. And once again, we have the same base, the same results. That can only happen if we have the same exponents. So that looks like 2x equals 4, implying that x is 2. We'll check it out. 8 to the 2 minus 1, that would be 8 to the first. 2 to the 2 plus 1, that would be 2 to the third. 2 to the third does equal 8. These last two got a little fancier. We need a common base, something that when we raise it to a power, it'll come out to 8, raise it to a different power, it'll come out to 2, raise it to a different power, it'll come out to 4. Now we already know for 8 and 2, our common base was 2. If 4 can also be written as a power of 2, then 2 will work for all three of them, which it does. Our common base here is going to be 2 again. So we know that 8 is 2 to the third. We know that 2 is 2 to the first. And we know that 4 is 2 to the second. So we're just going to substitute those in everywhere. Instead of 8, we're going to write 2 to the third raised to the x equals 2 to the seventh times, instead of 4, we're going to write 2 to the second raised to the ninth. And then just do some kind of simplifying here. So that's 2 to the 3x equals 2 to the seventh times 2 to the 18th. Because we're multiplying here, we can make this 2 to the 25th. This was not what I expected. So the only way this can work is if 3x equals 25. So x has to equal 25 thirds. That looks like we should check this. If we check it, that means 8 to the 25 thirds has to equal 2 to the seventh times 4 to the ninth. Okay. So that would be the cube root of 8, and we can say raised to the 25th, equals 2 to the 25th, because we know that that comes out to 2 to the 25th this side. Well, the cube root of 8 is 2. So it does indeed check out. The last one is a little weirder. We need something that when you raise to a power comes out to 27. You raise that same number to a different power, comes out to 1/9. Well, roots of 27 and 9, there aren't that many roots of 27 and 9, except 3. And we can do this. We can pick a common base of 3 to write our answers. So 27 is the same as 3 to the third. 1/9, now if it was just plain old 9, that would be 3 to the second power, 3 squared. But it's 1 over 9, it's the reciprocal of 9. So this is actually going to be 3 to the negative 2. And we just do the substitution again. Replace the 27 with 3 to the third. And that's being raised to the 1 minus x. Replace the 1/9 with 3 to the negative 2, which is being raised to the 2 minus x. Yay! Powers of powers, we have 3 to the 3 minus 3x equals 3 to the negative 4 plus 2x. That means 3 minus 3x has to equal negative 4 plus 2x. So it looks like negative 5x equals negative 7x is 7/5. And we should probably check it. So 27 to the 1 minus 7/5 is supposed to equal 1/9 to the 2 minus 2/5. I'm sorry, 2 minus 7/5. Lovely. 27. So this is 5/5 minus 7/5 to the negative 2/5 equals 1/9. So 2 whole numbers is 10/5. Subtract 7 is 3/5. Oh, yes. Wow. So this is going to be 1/27 to the positive 2/5. So that's the 5th root. Whoa. The 5th root of 1/27 squared is supposed to equal the 5th root of 1/9 cubed. And 27 squared and the third power on 9 are both 729. So this does check out. I hope they won't all be that nasty, but I'm asking you to please try the next two, and when you finish, come back and check your answers.